Each one looks like a line, something with only a single dimension. But suppose we could explore one of these cables way up close, like from the point of view of an ant. Now, a second dimension, which wraps around the cable, becomes visible. From its point of view, the ant can move forwards and backwards, and it can also move clockwise and counterclockwise.
So, dimensions can come in two varieties. They can be long and unfurled, like the length of the cable, but they can also be tiny and curled up, like the circular direction that wraps around it.
Kaluza and Klein made the wild suggestion that the fabric of our universe might be kind of like the surface of the cable, having both big extended dimensions, the three that we know about, but also tiny curled up dimensions, curled up so tiny, billions of times smaller than even a single atom, that we just can't see them. And so our perception that we live in a universe with three spatial dimensions may not be correct after all. We really may live in a universe with more dimensions than meet the eye.
So, what would these extra dimensions look like? Kaluza and Klein proposed that if we could shrink down billions of times, we'd find one extra, tiny, curled-up dimension located at every point in space. And just the way an ant can explore the circular dimension that wraps around a traffic light cable, in theory, an ant that is billions of times smaller could also explore this tiny, curled-up circular dimension. This idea that extra dimensions exist all around us lies at the heart of string theory. In fact, the mathematics of string theory demand not one, but 6 extra dimensions, twisted and curled into complex little shapes that might look something like this.
If string theory is right, we would have to admit that there are really more dimensions out there. And I find that completely mind-blowing.
If I take the theory as we have it now literally, I would conclude that the extra dimensions really exist. They're part of nature.
When we talk about extra dimensions, we literally mean extra dimensions of space that are the same as the dimensions of space that we see around us. And the only difference between them has to do with their shape.
But how could these tiny, extra dimensions, curled up into such peculiar shapes, have any effect on our everyday world? Well, according to string theory, shape is everything. Because of its shape, a French horn can produce dozens of different notes. When you press one of the keys, you change the note because you change the shape of the space inside the horn where the air resonates. And we think the curled-up spatial dimensions in string theory work in a similar way. If we could shrink down small enough to fly into one of these tiny, 6-dimensional shapes predicted by string theory, we would see how the extra dimensions are twisted and curled back on each other, influencing how strings, the fundamental ingredients of our universe, move and vibrate. And this could be the key to solving one of nature's most profound mysteries. In 1995, string theorists from all over the world gathered at the University of Southern California for their annual conference. Ed Witten showed up at Strings 95 and rocked their world.
I was really trying to think of something that would be significant for the occasion. And actually, since 5 string theories was too many, I thought I would try to get rid of some of them.
To solve the problem, Witten constructed a spectacular new way of looking at string theory.
Ed announced that he had thought about it, And moreover, he had solved it. He was going to tell us the solution to every string theory in every dimension, which was an enormous claim. But coming from Ed, it was not so surprising.
The atmosphere was electric because all of a sudden, string theory, which had been going through kind of doldrums, was given an incredible boost, a shot in the arm.
Ed Witten gave his famous lecture, and he said a couple of words that got me interested. And for the rest of the lecture, I got hooked up on the first few words that he said and completely missed the point of his lecture.
I remember I had to give the talk after him, and I was kind of embarrassed too.
Ed Witten just blew everybody away.
Ed Witten blew everybody away because he provided a completely new perspective on string theory. From this point of view, we could see that there weren't really 5 different theories. Like reflections in a wall of mirrors, what we thought were 5 theories turned out to be just 5 different ways of looking at the same thing. String theory was unified at last. Witten's work sparked a breakthrough so revolutionary that it was given its own name, M-theory, although no one really knows what the M stands for.
What is the M for?
M-theory.
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 M-theory is a theory.
I don't actually know what the M stands for.
Well, the M has...
I've heard many descriptions.
Mystery theory, magic theory.
It's the mother theory.
Matrix theory.
Monstrous theory. I don't know what Ed meant.
M stands for magic, mystery, or matrix, according to taste.
I suspect that the M is an upside-down W for Witten.
Some cynics have occasionally suggested that M may also stand for murky, because our level of understanding of the theory is in fact so primitive. Maybe I shouldn't have told you that one.
Whatever the name, it was a bombshell. Suddenly, everything was different.
There was a lot of panic, if you like, realizing that big things were happening and all of us not wanting to get left behind in this new revolution of string theory.
After Witten's talk, there was renewed hope that this one theory could be the theory to explain everything in the universe. But there was also a price to pay. Before M-theory, strings seemed to operate in a world with 10 dimensions. These included 1 dimension of time, the 3 familiar space dimensions, as well as 6 extra dimensions, curled up so tiny that they're completely invisible.
Well, we think these extra dimensions exist because they come out of the equations of string theory. Strings need to move in more than 3 dimensions. And that was a shock to everybody, but then we learned to live with it.
But M-theory would go even further, demanding yet another spatial dimension, bringing the grand total to 11 dimensions.
We know that there have to be 11 dimensions for this theory to make sense. So there must be 11 dimensions. We only see 3 plus 1 of them. How is that possible?
For most of us, it's virtually impossible to picture the extra higher dimensions. I can't. And it's not surprising. Our brains evolved sensing just the 3 spatial dimensions of everyday experience. So, how can we get a feel for them? One way is to go to the movies. We're all familiar with the real world having 3 spatial dimensions. That is, anywhere I go, I can move left, right, back, forth, or up, down. But in the movies, things are a bit different. Even though the characters on a movie screen look 3-dimensional, they actually are stuck in just 2 dimensions. There is no back, forth on a movie screen. That's just an optical illusion. To really move in the back fourth dimension, I'd have to step out of the screen.
And sometimes moving into a higher dimension can be a useful thing to do. So, dimensions all have to do with the independent directions in which you can move. They're sometimes called degrees of freedom. The more dimensions or degrees of freedom you have, the more you can do. That's right. And if there really are 11 dimensions, then strings can do a lot more too.
People found fairly soon that there were objects that lived in these theories, which weren't just strings, but were larger than that. They actually looked like membranes or surfaces.
The extra dimension Witten added allows a string to stretch into something like a membrane, or a brain for short. A brain could be three-dimensional, or even more. And with enough energy, a brain could grow to an enormous size. Perhaps even as large.
These theories, which weren't just strings, but were larger than that. They actually looked like membranes or surfaces.
The extra dimension Witten added allows a string to stretch into something like a membrane, or a brain for short. A brain could be three-dimensional, or even more. And with enough energy, a brain could grow to an enormous size. Perhaps even as large as a universe. This was a revolution in string theory.
String theory has gotten much more baroque. I mean, now there are not only strings, there are membranes. People go on calling it string theory, but the string theorists are not sure it really is a theory of strings anymore.
The existence of giant membranes and extra dimensions would open up a startling new possibility. That our whole universe is living on a membrane inside a much larger, higher dimensional space. It's almost as if we were living inside a loaf of bread. Our universe might be like a slice of bread, just one slice in a much larger loaf that physicists sometimes call the bulk. And if these ideas are right, the bulk may have other slices, other universes that are right next to ours, in effect, parallel universes. Not only would our universe be nothing special, but we could have a lot of neighbors. Some of them could resemble our universe. They might have matter and planets and, who knows, maybe even beings of a sort. Others could certainly be a lot stranger. They might be ruled by completely different laws of physics. Now, all of these other universes would exist within the extra dimensions of M-theory, dimensions that are all around us. Some even say they might be right next to us, less than a millimeter away. But if that's true, why can't I see them or touch them?
If you have a brain living in a higher dimensional space and your particles, your atoms, cannot get off the brain, it's like trying to reach out, but you can't touch anything. It might as well be on the other end of the universe.
And it's a very powerful idea, because if it's right, it means that our whole picture of the universe is clouded by the fact that we're trapped on just a tiny slice of the higher dimensional universe. And it's a very powerful idea, because if it's right, it means that our whole picture of the universe is clouded by the fact that we're trapped on just a tiny slice of the higher dimensional universe.
It is a powerful idea, especially because it may help solve one of the great mysteries of modern science. It has to do with gravity. It's been more than 300 years since Isaac Newton came up with the universal law of gravity, inspired, as the story goes, by seeing an apple fall from a tree. Today it seems obvious that gravity is a powerful force.
It would seem to most people that gravity is a very important force. It's very strong. It's very hard to get up in the morning, stand up, and when things fall, they break because gravity is strong. The fact of the matter is that it's not strong. It's really a very weak force.
Gravity pulls us down to the Earth and keeps our Earth in orbit around the sun. But in fact, we overcome the force of gravity all the time. It's not that hard. Even with the gravity of the entire Earth pulling this apple downward, the muscles in my arm can easily overcome it. And it's not just our muscles that put gravity to shame. Magnets can do it too, no sweat. Magnets carry a different force, the electromagnetic force. That's the same force behind light and electricity.
It turns out that electromagnetism is much, much stronger than gravity. Gravity, in comparison, is amazingly weak. How weak?
The electromagnetic force is some 1,000 billion, 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 billion times stronger. That's a 1 with 39 zeros following it.
The weakness of gravity has confounded scientists for decades. But now, with the radical world of string theory, filled with membranes and extra dimensions, there's a whole new way to look at the problem.
One way of approaching the question of why gravity is so weak compared to all the other forces is to turn the question completely on its head and say, no, actually gravity isn't very weak compared to all the other forces. It just appears to be weak.
It may be that gravity is actually just as strong as electromagnetism, but for some reason, we can't feel its strength.
Consider a pool table, a very large pool table. Think of the surface of the pool table as representing our three-dimensional universe, although it is just two-dimensional. And think of the billiard balls as representing atoms and other particles that the universe is made out of.
So here's the wild idea. The atoms and particles that make up stuff in the world around us will stay on our particular membrane, our slice of the universe, just as the billiard balls will stay on the surface of the pool table. Unless you're a really bad pool player. But whenever the balls collide, there is something that always seeps off the table. Sound waves. That's why I can hear the collision. Now, the idea is that gravity might be like the sound waves. It might not be confined to our membrane. It might be able to seep off our part of the universe. Or think about it another way. Instead of pool tables, let's go back to bread. Imagine that our universe is like this slice of toast, and that you and me and all of matter, light itself, everything we see, is like jelly. Now, jelly can move freely on the surface of the toast, but otherwise it's stuck. It can't leave the surface itself. But what if gravity were different? What if gravity were more like cinnamon and sugar? Now, this stuff isn't sticky at all, so it easily slides right off the surface. But why would gravity be so different from everything else that we know of in the universe? Well, it turns out that string theory, or M theory, provides an answer.
It all has to do with shape. For years, we concentrated on strings that were closed loops, like rubber bands. But after M-theory, we turned our attention to other kinds. Now we think that everything we see around us, like matter and light, is made of open-ended strings. And the ends of each string are tied down to our three-dimensional membrane. But closed loops of string do exist. And one kind is responsible for gravity. It's called a graviton. With closed loops, there are no loose ends to tie down, so gravitons are free to escape into the other dimensions, diluting the strength of gravity and making it seem weaker than the other forces of nature. This suggests an intriguing possibility. If we do live on a membrane, and there are parallel universes on other membranes near us, we may never see them, but perhaps we could one day feel them through gravity.
If there happens to be intelligent life on one of the membranes, then this intelligent life might be very close to us. So theoretically, and purely theoretically, we might be able to communicate with this intelligent life by exchanging strong gravity wave sources. Then this intelligent life might be very close to us. So theoretically, and purely theoretically, we might be able to communicate with this intelligent life by exchanging strong gravity wave sources.
So who knows, maybe someday we'll develop the technology and use gravity waves to actually communicate with other worlds. Yeah, hey, it's Brian. How you doing?
Brian. Jerry Woofalapa Jabba Simpsons.
We don't really know if parallel universes could have a real impact on us. But there is one very controversial idea which says they've already played a major role. In fact, it gives them credit for our existence.
As the classic story goes, the vast universe we see today was once extremely small, unimaginably small. Then, suddenly, it got bigger. A lot bigger during the dramatic event known as the Big Bang. The Big Bang stretched the fabric of space and set off the chain of events that brought us to the universe we know and love today. But there's always been a couple of problems with the Big Bang theory. First, when you squeeze the entire universe into an infinitesimally small but stupendously dense package, at a certain point, our laws of physics simply break down. They just don't make sense anymore.
The formulas we use start giving answers that are nonsensical. We find total disaster. Everything breaks down, and we're stuck.
And on top of this, there's the bang itself. What exactly is that?
That's actually a problem. Classic form of the Big Bang theory really says nothing about what banged, what happened before it banged, or what caused it to bang.
Refinements to the Big Bang theory do suggest explanations for the bang, but none of them turn the clock back completely to the moment when everything started.
Most people come at this with the naive notion that there was a beginning, that somehow space and time emerged from nothingness into somethingness.
Well, I don't know about you, but I don't like nothing. Do I really believe that the universe was a big bang out of nothing? And I'm not a philosopher, so I won't say, but I can imagine to a philosopher that is a problem. But to a physicist, I think it's also a problem.
Everyone admits there are problems. The question is, can string theory solve them? Some string theorists have suggested that the Big Bang wasn't the beginning at all, that the universe could have existed long before, even forever. Not everyone is comfortable with the idea.
I actually find it rather unattractive to